Hello everyone, hope you guys are doing well. On this video we're going to continue with the intermolecular forces. So let's get into it. So let's compare first of all what is the difference between the intermolecular and intramolecular forces. So as you see in here we have a water molecule on the left side, and the bonding that we know for water is going to be, we have this bond called covalent bond. This covalent bond is intramolecular force. So this force is within the molecule. Okay? But when we have intramolecular forces, it is the force between two molecules. Okay, I have one molecule here and I have another one here, and the force that keeps them together, this is called intermolecular forces. So this would be between different molecules. So for intermolecular forces we have covalent and ionic bondings. And of course you know that intramolecular forces, molecular forces will be stronger than intermolecular forces, because when we, for example, I'm going to give you example. When we boil the water, we break the intermolecular forces, but we cannot break intramolecular forces in normal conditions. Okay, so when we boil the water, we break down all the intramolecular forces, but intermolecular forces are still there. The bubbles, the steam is still water. It is still a water. This liquid is a water too. And the bond that keeps them together is still going to be there. That's why this bond is strong. Okay, now the types of intermolecular forces. We have in here the three types. One is the London dispersion, and the other one is dipole-dipole and hydrogen bonding. Their strengths are like this. The London dispersion is weaker than dipole-dipole, and they're all weaker than hydrogen bonding. In some of the literatures, they say this London dispersion and dipole-dipole altogether, it is called van der Waals. Okay? Now we're going to discuss what is London dispersion forces. So this has nothing to do with City of London, okay? It is the surname of a scientist who found it. Who discovered this. Okay, so I'm going to give you an example. Let's say we have a non-polar helium atom, okay? We have a nucleus in the middle. And we have electron clouds. Okay, we have electron clouds around. At one point, we have more electrons on this side. Okay, and we have less electrons. We will have less electrons on this side. It's just they are circulating, right? So for 1 second, we take take the picture, and it looks like because of this electron cloud we have a negative charge, partial negative charge and partial positive charge here. Okay, and when you have a partial negative and partial positive, you have another nearby helium atom. This is helium and this is helium 2. So this gets pulled by a positive, okay? And then you have another one where you have a partial negative and partial positive, and this is pulled by another one, okay? So we can say that London dispersion forces are instantaneous dipoles, okay? Instantaneous means momentary, okay, momentary, for a moment. Now, in the bottom it says London dispersion forces are instantaneous dipole-induced dipole forces. So the reason is due to temporary asymmetries. For example, we have here a symmetry, okay, of electron cloud. And this temporary asymmetries in electron distribution, all molecules experience London dispersion force. So this is very important. Everyone experiences London dispersion force. Now, we have a video here. Try to check it out. I believe it's not working anymore, so if you don't see it, it's the same thing as I just explained. Now, London dispersion reading material. Again, we have protons in the middle, and then you see we have electron clouds. Electron clouds, they're not always, spread out evenly. They change. And then when you have varying changes in your electron cloud, you can have partial negative and partial positive on one side, and this will get pulled by partial positive of the other element, of the other molecule. All molecules experience London forces. London forces depend on number of electrons. So number of electrons. That means that the more electrons you have, more electrons you have, stronger London forces you have. Okay? Area from the nucleus. So long molecules with large surface area will experience larger London forces than a spherical molecule. Okay? So let's say if you have a molecule, let's say like this, okay? This is hexane. You will cover this in 11th grade. So this is a long molecule. And let's say I have another cyclohexane. I will have cyclohexane. This is like a cycle, you see? So this guy is long, while this guy is spherical. Now, this one here will have larger London force because of surface area. Even though they have same amount of electron. But because of the surface area, this guy have a larger London force. So before I finish off, so I told you more electrons means you have a stronger London force, right? So on periodic table, when we go, for example, in the last one, you have helium and then neon and then argon. As you go down, number of electrons increase, because we know that atomic number increases, right? Atomic number increases. So as you go down, London forces increase, which cause your boiling point to increase. Okay, so if we check the P table, you will see that as we go down, the boiling point, for example, for helium is minus 259. For this one is going to be minus 230 something, and then it will go even further, and then on the last one it will be 104. So as you go down, this is all centigrade. So as you go down, the boiling points are increasing. Okay, when your London forces are increasing, you see what I'm saying? In here, when I have the bond here, that gets stronger. It is hard to break the bond, break the IMF, which is intermolecular force. But when you boil, when you put heat, for example, when you put heat, you try to break IMF, intermolecular force. But once your London force goes up, your boiling point will go up as well, because it is harder to break those bonds. Is this clear? I hope it is clear. So now we're gonna continue with the dipole forces. Now dipole forces are permanent. They are not temporary like London force. They are not temporary. They are permanent. So let's say we have hydrochloric acid, and we have a chlorine here, hydrogen. This is covalent bond in the middle, but this is intramolecular force. We don't care about it at this point. We care about this force, which is IMF. Chlorine, we know that it is more electronegative, higher electronegativity. So it will withdraw electrons closer to himself, will make himself a partial negatively charged. And hydrogen, because it will give away electrons, it will become partially positive. And then we have another hydrochloric acid which have the same charges in here. And this one is permanent polarization here, right? So this will withdraw, this negative will draw positive, and we will have always this in here. You see how we have close distances between them? It is all because of IMF, which is intermolecular forces. So dipole forces are attraction between positive end of one permanent dipole and the negative end of another permanent dipole on adjacent molecule. So again, as your IMF intermolecular, as IMF is increasing, boiling point and melting point will increase. Okay, now let's read this. We have dipole forces occur in all molecules with permanent dipole moment. Okay, so when you have electronegativity difference more than 0.5, you have dipole. But if it is less than 0.5, you only have London dispersion. Okay, so London dispersion happens to all molecules. But this one only happens for polar molecules. Polar molecules. Polar molecules with polar bonds. Polar with polar bonds. So, an attraction between positive end of one permanent dipole and the negative end of another permanent dipole. So you guys have this molecule provide a weak intermolecular forces. They called it weak, but generally, if you look at here, London dispersion is weaker than dipole-dipole, and it is weaker than hydrogen bonding. Now we're going to cover the hydrogen bonding. So I want to say before this, so if you have a molecule, if you have a molecule with dipole-dipole, you ignore the force coming from London dispersion. The reason is London dispersion is weak. Once you have a dipole-dipole, you know that you have a stronger IMF than London dispersion, so you don't care about this one. But let's say when you have a hydrogen bonding and you don't care about the IMF of the dipole-dipole or London dispersion, okay? So depending on which one you have. So hydrogen bonding is happening when you have these elements: N, nitrogen, oxygen, and fluorine. And this happens like this. I'm going to show you here. So I need to have a bond of OH, I need to have a bond of NH, or I need to have a bond of FH. If I don't have this, I don't have a hydrogen bonding. So this is needed for hydrogen bonding. For example, if I have a molecule of water, because oxygen is more electronegative, it will be partially negative, and this will be partially positive, this will be partially positive. And then I have another oxygen, another water, and then I have another water. So the same idea of partially negative, partially positive, partially positive, partially negative, partially positive, partially positive. So this bond is happening between them. You see, this is positive, this is negative. And this is happening with this guy, and there is a bonding happening with this guy. So there's a lot of bonding happening. And then I will show you another one for nitrogen. Let's say I have ammonia, NH3, and then I got another NH3, and then I have one more NH3. So now we know that nitrogen is more electronegative, and then hydrogen is positively charged in this case. Okay, so now positive will attract negative, so we know that this will attract this. This attracts this, and then I have this will attract this, and then I have this will attract this. So the same idea. And now I'm going to show you with fluorine. For example, I have here hydrogen fluoride, and then I have hydrogen fluoride, hydrogen fluoride, hydrogen fluoride. So I know that this is partially negative, partially positive, because fluorine is more electronegative. Okay, and then I have this bonding happening here. Okay, so this bonding happening, these are all hydrogen bonds, but I showed you different versions. So whenever you see this, you know that you have hydrogen bonding. Okay, now we have a compound, we have elements and compounds given to us, and we're gonna discuss which kind of intermolecular forces they have, intermolecular forces. So neon, we know that there is no nitrogen, oxygen, or fluorine, so we don't have any hydrogen bonding on this guy. We know that neon is only made out of neon, so we don't even have a dipole-dipole. But we have on this guy London dispersion force, because London dispersion happens to everyone, okay? And then we have another guy, and look at here. Let's say CH2F2. If we do the Lewis dot diagram of this, you guys will see that it'll be H in here, fluorine with this, and then I got fluorine with 6 electrons like this. And then you know that fluorine is more electronegative, right? So it'll be partially negatively charged, and this will be partially negatively charged. And carbon in this case will be partially positively charged. Okay, so this is partially positively charged, and I have another of this guy, which is nearby. So I'm just gonna draw one more. Okay, and then this is partially negative, and this is partially negative. And in this case, the hydrogen will be partially positive too, before I forgot. So partially positive, partially positive, partially positive. So this and this will start drawing each other. There will be a bond here, and we will have another bond coming from here, from this guys, and this one is gonna be called dipole-dipole. Okay, and then so I'm just gonna delete this part, and now we have this guy left in here. We know that this guy has a bonding, so CH3, CH2, and then we got NH2, and NH is like this. So we have here nitrogen and hydrogen bond. I told you nitrogen is gonna be the hydrogen bonding. So if I'll draw another one here, nitrogen and hydrogen, I know that nitrogen is partially negative, this is partially positive, this is partially positive, partially negative, partially positive, partially positive. I know that this is gonna be drawn by this guy, and this will be drawn by this guy. So we will have here hydrogen bonding. Okay? But if you take them into account, we know that all of them have London dispersion force. But I told you that if we have dipole-dipole 2, we don't care about London dispersion. So the first guy will have a London dispersion, and the second guy, even though he has London dispersion and he has dipole-dipole, we only take into account dipole-dipole. And then the last guy has hydrogen bonding and has London dispersion and dipole-dipole, but we only take into account hydrogen bonding because hydrogen bonding is stronger than any other. Okay, so now we have, for the first one, for neon we have London dispersion. For CH2F2 we have dipole, and for this last molecule we have hydrogen bonding. Just going to make it in a different color. This is hydrogen bonding. Okay, and if you assign them in, let's say, boiling point, they will ask you to put them in an increasing boiling point, increasing order, or melting point. You will put neon, and then you will put CH2F2, and then you will put CH2 and H2, because the last one, hydrogen bonding, is stronger than dipole, and dipole is stronger than London dispersion. Okay guys, now we're going to continue with metallic bonding. So before we go ahead, I want to make sure that we know that in periodic table we have mostly metals, right? Metals. And metals lose electron because their ionization energy is low. So when you have metal, it's easy for him to lose electron and become positively charged, right? So you have a lot of positively charged metals, and they have electrons around. These are their electrons. We have lots of electrons in any metal. And when you have a free cloud of electrons moving around, it makes metals to conduct electricity and heat very easily. Now, let's read the stuff that is given to us. Metals, when they are solids, they have a regular crystalline lattice structure with positively charged ions. So I told you that we have electrons and we have positively charged ions. And in the units of lattice and electrons that move randomly between these units. So you can see that electrons are moving freely. They move anywhere they want. Okay? And when you have electron which is negatively charged and metal ions that are positively charged, they attract each other. Okay? They start attracting each other and makes metallic bonding. Okay? So this happens the same way. Electrostatic force. A chemical bond formed through electrostatic attractive forces, because you have positive and negative charged metal ions and freely moving electrons. Now, metals can have metallic bond in a pure form like metals, or in alloys. Alloys is a mixture of metals, such as steel. You know that steel is made of different metals. It's not just iron. It is made of different metals. And please pay attention here. It says that under electric charge, they obtain one direction. In normal condition, electrons are chaotic. This will be explained in this picture. So this is the normal condition. So you see here, electrons are moving wherever they want. But once you pass electricity, you send electricity inside. You know, like we have wires, right, in everywhere. You put electricity inside, and then you will see that electrons are moving in one direction. You see, they're all moving one direction. This all free ions, free electrons are moving in one direction. So Now, we know that metals conduct electricity and heat because of free electrons. When you have free electrons, you can conduct electricity. But when you don't have free electrons, you don't conduct. For example, in ionic bonding, do you remember we talked like solid state? In solid ionic bonding, do not conduct electricity. For example, sodium chloride. At home, we have it salt, right? It's solid. When you put electricity, it won't conduct, will not conduct. Because conduct. Now I'm going to give you very important message, because no free electron. You need free electron for electrical conduction. If you don't have free electron, you cannot conduct electricity, nor you cannot conduct electricity nor heat. Okay? You need free electrons. So now we have two metals in here. Look at their shape. Look how they are looking like. It's shiny, right? They are shiny. Let's read this. This is called, the shininess is called lustrous. Okay, when you're shiny, you have a lustrous structure. So, electrons of the last shell in metals are not completely bound to any individual atom, are relatively free. I told you, we have a free electrons. That's why we conduct electricity and heat. Heat and electricity. These electrons are concentrated on the surface, tend to oscillate at collective frequency. Oscillation meaning that they just like move around, okay, freely. When they oscillate, they prevent any incoming light from entering the metal or transmitting through. So when you have electrons around here, when there is a light, for example, light coming in here, this electrons do not let the light to pass through. They do not. They just block it and they reflect it back. When sunlight comes in to metal, we know that metals are shiny, right? The sunlight just reflects back. It does not go inside. It doesn't pass through. So that's why light is reflected back. The intensity of this reflection of light reaching our eyes makes it appear lustrous. So I told you, when you're looking at the metal here, right? Look at this guy. It looks like he's super shiny, right? Because light cannot go through inside. It just reflects back. And that's what it makes it shiny, because we have electrons inside it that doesn't let this guy light to go inside. Okay? Does not let it go. So, properties of metals, ductile and malleable. We already tested with the hammer some of the metals, right? So when you hit it with the hammer, you see the one in here. When you hit it with the hammer, I got here positive ions of metals, right? And I have here electrons, you guys see. When I hit it with the hammer, it just changed the shape easily, right? But it does not like shatter, doesn't crack when you have metal bonding. Now let's read it why. Metals are malleable and ductile because of the non-directionality of the bonding. I told you that electrons are attracted by metal ions in the lattice and in all directions. So you see all the ions, they're just chaotic. They're moving everywhere, right? And when you hit it with the hammer, you can just make it you can change the shape. But because electrons are just like not going in one direction, it's not going to crack. Everything is going to be in one place. That's why we call them malleable. And the same reason ductile. Ductile means that you can make it into wires. Like you can grab a metal and you can make it thin like this. And you can make wires and cables out of it. Okay? And that is the reason because we have in the lattice is this, the crystallic shape. So in the lattice, you have free electrons that move. This is the important one, that move in all directions, okay? In all directions. Metal ions in all directions. I'm just gonna clean this part and I'm gonna mark the very important part. So metal ions in the lattice that move in all directions, which makes it ductile and malleable. And then if layers of the structure slide or bend, the bonding in the resulting structure is the same. So look at this, guys. Okay, so when I hit it here, these are gonna start moving down, right? If I start hitting from this side, this start moving, but because electrons are moving freely, metal is not gonna change the shape. So even if you look at this coin, okay, because I have free ions, I can bend it either way, whichever way I want. I can use this equipment and press it in a way that I want. So now we're going to talk about the properties of metals. I want you to really bear in your mind, whenever you have a bonding happening, you have melting point and boiling point going up, increasing, okay, increase. Because this bonding is protecting you. And melting and boiling points show you how strong is your bonding. For example, I got here sodium and magnesium. Sodium has, you see, we know that sodium is a first group element and it will make sodium plus and electron will get out. So you have one electron, you see. But magnesium is a second group to A group, so magnesium will make plus 2 charge. So he will have more free electrons. So which one do you think has a stronger metallic bond? Of course, it will be magnesium because he has more free electrons. When you have more free electrons, you will make a stronger metallic bonding. Metallic bonding. And look at the temperatures. The T melting of sodium is 98 degrees, and the boiling point of sodium is 883. Now look at the magnesium. His melting points are higher, and boiling points are higher. It is all because of the stronger metallic bonding. Okay? So now look at here, we have metals often have high melting and high boiling points. We know this. Metals melt at higher temperatures and boil at higher temperatures. The only exception is mercury is the only metal that is liquid at normal temperature. We know it. We have it inside the thermometer. And cesium and gallium melt when you take into hands. And I will explain you why. And then we have tungsten. Look at the melting points, so high. Why magnesium has higher melting points than sodium? I told you, magnesium has a plus 2 charge, number of free electrons is greater, and the radius of magnesium is smaller. Now I want to explain you about the radius. If you guys remember, we talked about the atomic radiuses, and then I'm going to show you, for example, here. On this one, we said that atomic radius is increasing in which fashion? If you guys remember. Okay, so we know that atomic radius is increasing from right to left and from top to bottom, right? It is increasing. This is atomic. Also the same for ionic radius. So now let's compare sodium and magnesium. Sodium will have a larger radius than magnesium, okay? And as you go down, radiuses are even increasing. Rubidium is even bigger, cesium is even bigger, so it's increasing as you go down. Now I want you guys to pay attention. When I have, for example, an atom, or let's say ion I have, and I have electrons around here, right? If I have a bigger radius, which one do you think will attract it better? Because positive sign comes from the nucleus, right? Positive comes from the nucleus. When I have positive sign in a smaller ion, I will attract electron better because I have less distance. Here. But when I have a bigger radius, I have more distance. So it's kind of hard for me to attract electrons. So now you could say that as you go down, because atomic radius is increasing, is increasing. Metallic bonding will decrease too. So metallic bonding decreases as you increase atomic radius. Now we're going to go back and we will cover this. The greater radius of magnesium, the radius of magnesium is smaller than sodium, because we know that sodium has a bigger radius than magnesium. They look like this, okay? And then this is plus, and this is negative electrons, right? Because magnesium has a smaller radius than sodium, magnesium will have higher boiling point and melting point because of metallic bonding. Also, this is one factor, and the other main factor is number of free electrons. Because magnesium becomes magnesium plus 2, and then sodium becomes sodium plus 1, sodium loses 1 electron, while magnesium loses 2 electrons. So you have more electrons, so you have a stronger metallic bonding. Okay? So all these factors, they make positively charged metal ions and electrons stronger and thus harder to break. Okay, so now the final thing is the allies. So for example, all these coins you guys see here, they are all allies. They are mixtures, okay? Mixtures. For example, bronze, the ones that you see in the Olympic medal ceremony, they are made of copper and tin. For example, 18K gold, look at how it's made 75% of pure gold, and we got copper and silver. Cast iron, it is made out of iron and carbon. Cast iron is the one that you use, at home to cook your food on, like a really heavy pans. Okay, those are cast irons. And then you have stainless steel, like for example your cutlery. They are made of this guy. Brass is another type of metal used in industry. And then we got sterling silver. They are all mixtures. And alloys also have free electrons. Okay? That's why, and the reason they use these ones for example, coins is because it is cheaper to use mixture. Also because they are hard to break because of, as said again, because of metallic bonding. So I know it's a funky sentence. Cheaper to use, that's a one reason. And then they are hard to break because of metallic bonding. So now let's read this through. Alloys are homogeneous mixtures of metals with one another, or nonmetals. Alloys tend to be stronger, stiffer than pure metals. Due to atoms with different size and structure is not ideally regular, and sliding layers of atoms is less likely to happen. So when you have a different size of atom, it's less likely that they're going to break. Alloys are made to reach desirable properties of materials. So you mix it up in a way, you see all these percentages. People have done it throughout the history, and they found the perfect composition. They said that, okay, this is the perfect composition for stainless steel. It is cheaper, and we can actually make this. For example, aluminum is light, but not strong. Thus, it is mixed with the copper and some other elements to become more durable. With good properties and desired properties also come. For example, duraluminum alloy from previous paragraph is more subjected to corrosion than pure aluminum. So pure aluminum is gonna have corrosion. Like on the layer, you will see corrosion. But when you make alloy, you can prevent the corrosion. Okay, that's it, guys, for the metallic bonding. Overall, all of this bonding. I hope this helps. Good luck.